First, let's see the core Newton method. So the data set is actually very recent, released in July 2020. And as you can see, the description of the data set, most of the values are binary. And we have to predict whether we have diabetes, like whether the person have diabetes or not. And like these are the tasks, all tasks are related to implementing logistic regression for Newton method. Okay. So the imports are very straightforward. NumPy and pandas as always for numerical operations. Train test split to split the data set, logistic regression for verifying our approach that how much close we are to the scikit-learn. Accuracy score to compute the accuracy, min-max scaler to pre-process the continuous value columns. Okay, let's run that. Read the data set. And this line is again for the intercept column. So insert 0 means at position 0, intercept the name of the column. 1 means what value you want to insert. True means that I don't care about whether it's the data set has duplicates or not. So data can have duplicates. So let's print first 5 and last 5 rows. So here what we can observe. We can observe that we got the intercept column, and the age column is the only column which is continuous. Other all columns are binary values. So as you can see, no and yes columns are, all the columns are no or yes. Only gender column is female and male, and class is positive, negative. All right. So let's handle the categorical values now. So this is this is the fastest way of doing yes no column to 0 1. So I initialize the list comprehension where intercept, age, gender, class, except all these columns. I mentioned all the columns which are yes no, and this is the line. So what I say is np.where. So where the values are yes, where the yes no columns have value yes, mark them as 1, otherwise 0. So this is the syntax. Condition value if truth, value if false, right? And it will return you a Boolean array. Boolean array means only true and false values. The transformed array where you have 1 and 0. And then I convert that into data frame. Simple. And then I just assign that to yes no columns again. So this is the fastest way of doing yes no columns to 1 0. Like there are other ways also, but this is the fastest way. Other way of converting binary to 1 0 is using map function of pandas. So data gender dot map. So what to map with? You have to feed it into a dictionary. So I'm feeding a dictionary, making a dictionary where female is 1 and male is 0. Similarly, class variable, I'm mapping a dictionary, positive is equal to 1 and negative is equal to 0. Now, so you can see all the binary columns are transformed to 1 0. So this is the fastest way of doing things. Map is also closer in time complexity with np.where. There are other also ways like apply map is there. There is dot apply function is also there. But those functions are like they can do much more complex things because like dot apply is there. Like for example, data class dot apply function is there, which takes a function in. And so you can apply any function to any column. So that is like more generalized. So these are like very fast operations. Okay. So next task was to normalize the age feature because like age is 1 to I think 15 to 60, I think something. So we have to convert that, normalize the column. So I use min-max scaler for that. Initialize it, call fit transform on that. So fit transform means we fit the R scalar according to the data age and also transform the data age column itself. So two functions combined in one function and then assign it. So we normalize it. Let's look at the data again. So it's normalized, right? Okay. Next task was to define X and Y. So this line simply says that all the variables except the class columns are X and class variable is Y. Train test split. we have to split in 60-40 ratio. So test size is 0.4 as we discussed. Next was the predict function. So predict function was very similar to the last. Actually, in fact, everything is same except the last line. Here we are not doing any fancy threshold thing. We are just taking the round. So round means 0.5 above it is 1 and 0.5 below it is 0. I'm sorry. Right, so rest predict was that this is hypothesis and we apply sigmoid. So that's how we get logits, and y prediction is simply the round function. So that's how we predict. Sigmoid is all the same, so nothing to explain here. 1 divided by 1 plus exponential minus z. Next was the cross entropy loss. And here I will clarify the doubt also that what is plus, what is minus. And so like this line is same, except that epsilon is 1 e power minus 15. This is to fix 0, and 1 minus 1 is also 0. So this fixes that also. So this minus and minus. So in previous, we saw that it is plus. So log likelihood function it was. So we want to maximize log likelihood if we are doing gradient ascent. If we are doing gradient descent, then we need loss function. And it's just a different name. Like we are calling it cross entropy loss or binary cross entropy loss. But you can also call it negative log likelihood. Like you can call this function as negative log likelihood also. It is the same thing. So binary cross entropy loss is same as negative log likelihood. So that's why I just put a minus there, and it is converted into loss. Nothing else. Okay, now let's come to Newton optimization. So there were main two things in this. If you see the gradient and the Hessian, where many of you got, I think, stuck or have some questions about, but let's see like how we get started. So first we initialize the weights vector as always. Like you need weights for any machine learning parametric algorithm. So first we initialize the weights, then we start the iterations. And this again, like we need to have the predict probabilities so that we can do back propagation, or like you can do the gradient descent thing. So first we calculate this. Now for the gradient and Hessian, you need those formulas. So here's the formula for this: x transpose y p minus y. Now how we get this and like this values, like you might be wondering. Like first of all, this is the cross entropy loss that we have implemented. If you substitute yp with 1 upon 1 plus e minus x power w, you will get this. You can simplify this very easily on paper. To convert it to take the gradient, you need matrix calculus for this, that we studied in linear algebra. So as matrix calculus, I'll just give a brief intuition about it, not give much details in this session. We'll cover it in maybe in another session. But like just to give an intuition, this x transpose will come from this xw, because xw is like ax, and if we take with respect to x, it will be a transpose. So here we are taking with respect to w, so it is x transpose. Same from here, you will get x transpose. So that's why it's common. And from Hessian, this x you will get again from the same rule, because if you do this, then x transpose will become x. So that's why this x is here. And this x transpose will come from the chain rule, like when you do the gradient of this. And this diagonal will also come from the chain rule itself. I'm sorry. Yeah. So this diagonal will also come from the chain. So this is all matrix calculus, pure matrix calculus. There is nothing explicit about optimization or machine learning in it. It's pure matrix calculus for it. Okay, so we just simply substitute the formulas in NumPy. So np dot x transpose yp minus y. One thing I want to point out is, like usually in school we have studied that np dot is like element wise product and then you submit. But in np dot in NumPy, it means that it can also perform matrix multiplication, and it can sometimes also perform element wise. So when it performs what, you have to see the dimensions of it. So x dot transpose is like number of features into number of samples, and yp minus y is number of samples. So what you will get is like the matrix multiplication of these two. So you'll get as shape number of features is the shape of the gradient. Okay. Similarly, the Hessian the same. I just implemented the formula. Only the thing to note here is the np dot diagonal. So this is how you create a diagonal matrix into NumPy. Np dot diagonal yp into 1 minus yp and dot x. Okay, this line is the weight update line, which is the main whole point of Newton method. That like I can tell you that why we are taking inverse and gradient. Like I can give you an intuition that we are basically doing del j upon del square j is equal to the difference between the new weights and old weights. So to calculate del square 1 upon del square j, we use inverse of Hessian, and for del j it's gradient. So that's why we are doing np dot dot this. And
I think it's very difficult to sort of build an intuition for this. I myself face a lot of problem, and I think this will only be clearer once we know how the math works. Like right now, we're just only implementing the formula, I believe. I mean, you have done the maths, but it's very difficult to get an intuition for this.
Yeah, that's why I'm saying that we will cover the full mathematics in another session. But like we're also running out of time, so I can just only give you the intuition that why it was so. Like full mathematics, you have to do it on like pen and paper. Like we can cover it maybe later.
Yeah, we can just either share some videos or links later, maybe. But like for now, just like show how we're implementing the formula.
Yeah.
Himanshu, one thing you can do is for intuition, just maybe draw any function and show them how Newton descent is happening on that, if possible.
No, like it's complete mathematics only. There's nothing to like. It's same as the gradient, but different. Yeah, full matrix calculus you need to know.
Right. Let's say we will keep an altogether differentiation for the maths behind it.
Yeah, here I just wanted to point out the implementation parts, applied machine learning. So the main difference is I did not use np dot linear algebra in inverse. Instead, I use p inverse. Why? Because like many people were also facing the problem that with using inverse, you'll get an error for singular matrix. If determinant is 0, then you cannot calculate the inverse. So that's why we use p inverse for this. P inverse will say that if it is singular matrix, then it first like insert some random values in it, so it doesn't get determinant 0. So that's why we use p inverse. Like you can look at the formula that how it is calculated, pseudo Murray inverse we call it. Okay. So next is like simply we are appending the loss, calculating loss and appending to see that how we are converging. Okay, we have implemented this. Let's test it. Newton optimization and the loss curve. Okay, now you see that this loss curve is like converging at 5, converging only in 5 iterations. And if you see this, like it took 175 iterations. So there's a huge difference in how much time it converges, right? So this was the main difference. Let's calculate the accuracy. Okay, we get 0.903 on our test data. Okay, another thing I just wanted to point out is this time complexity and space complexity. In Newton method, like you can definitely observe that we have p cube and p square terms, but in gradient descent we have only np. I've copied this from this Medium link. I'll share this link. It's a good article. Please do give it a read. Space complexity is also higher and it is lower. So why do we use Newton method? Like time complexity is also higher, space complexity is also higher. Like you get the reason. It converges in 5 iterations. So there's a trade-off between the complexity and the speed of the algorithm. Okay, let's compare this with the scikit-learn implementation. So in scikit-learn for Newton method, you have to call this solver equals to Newton CG. There are 5 solvers in it. So Newton CG is one of them. Let's just train it, predict, and compute the accuracy. So 0.927 and we got 0.90. So pretty close, not that much closer, but I think it shows us that we have implemented correctly. It's close. Okay. So that was about the part 2.2. Now let me show you the if someone doesn't know like these values, like how do you get these values if you don't know? For example, like here we have only one function, cross entropy loss. If we have like sequential callback of 6 to 7 functions, then it is very difficult to compute this, right? So how does a practitioner or applied machine learner applies this? So let's look at that. So now we'll get back to 2.1. So first task says create matrix of size 10 into 10 with random integers. So I think we can do that very simply. And we pass in the size here, size of the matrix that you want to calculate. So I want 10, 10. Remember, it should be a tuple. If you pass like 10, 10 without tuple, then it will give an error. So let's look at matrix. So it is 10 cross 10 matrix with value between 0 and 1. So nice. So then it says find the inverse of the matrix and print it. So inverse of the matrix, as we have looked at, it is np.linearalgebra.inverse, and you pass in the matrix. So this is the inverse of that matrix. Simple. Next is the calculate dot product of the matrix with the same matrix in transpose. So as we have looked, np.dot means the matrix multiplication, and we have to dot this matrix with matrix.transpose. Right? 10, 10. So shape will 10, 10 into 10, 10, 10 into 10 will give me 10, 10. So if we also print the shape of it, it will be 10, 10. Okay, one thing we are doing very commonly is also multiplying with the vector, doing dot product with vector. So let me also show that how does that look like. So if I do dot with vector, it will be 10, because 10 into 10 into 10 into 1, so 10, 10 cancels out, 10 into 1 you get. And 1 is like pseudo thing, so it doesn't exist, so you get 10 comma. Okay. So next was the decompose the original matrix using eigen decomposition. So there is a function for this in the NumPy linear algebra, eig, and you just pass in the matrix. So it actually returns two things because we are asked eigenvalues and eigenvectors. So it returns two things. It returns eigenvalues, but it also returns eigenvectors. So let's look at each of them. See, look, there is also some imaginary numbers also. And we can verify our understanding of linear algebra that they occur in conjugate pairs. So like this and this occurs in conjugate pairs. So this is the eigenvalues. Similarly, like an eigenvector will be 10 cross 10. Because like we have 10 cross 10 matrix. Okay. Okay, so next thing was the Jacobian matrix, where many people got confused because we have not provided the cost function. But I think like you can take any cost function that you like. So that's why like we wanted to provide flexibility in this. So let's say like I have a cost function called like x cube, and it returns this. And next, like let me compute the cost of like 0.4 at 4. So it is 64. Now I want to calculate the Jacobian at this point. So how do I calculate that? So I can take like create a new function called this, and like I can say that it is 3 into x squared. Right? But this is like, if you know mathematics, then you can do it. If you don't know mathematics, then you cannot do it. So we will use a library for this, Autograd library I'm using, but you can use other libraries also. So let's calculate the Jacobian. Just wait a second. And pass in the function for which you want to calculate the Jacobian. So I want to calculate for the cost. Here. So Jacobian at 0.4 will be 48. And you can verify that 3 into x square. So 3 into 4 square, 3 into 16, That is 48, right? And now let's calculate the Hessian as well. Sir, that is actually, you have to pass one variable, but you can use like this. 0, we'll say that is x1, and then you can x1. Like this somehow. I'll show the vector thing also. Oh, no problem. For the cost for Hessian, if we calculate the Hessian now, so you can see the 24. So that will be 3x square derivative is 6x. So 6 into 4 is 24. So I think it's correct, Hessian. So that's how we do it. So it is not only about the single values, you can also pass in a vector. For example, you can also do one thing to be caution of, that Autograd needs autograd.numpy library. So you cannot use the usual numpy np. So either you can do like import autograd.numpy as np, and then you can like do np.sumxq. So now what I mean is that x is now a vector, like x can take a vector also. So let me pass in a vector here, like 4 vector should work. Let's calculate the Jacobian first. Okay, I'm sorry. Sequence box and integer. Yeah. So you have to pass in an array, not a list. So that is also a problem. Okay, now as you can see, the result is same 48, and Hessian also should be same 24. Okay, let me show you a key difference now. If I pass in another variable, 2 dot Jacobian, and let me calculate the Hessian now. You can see the difference at point 2. Like Jacobian is like, okay, it is same dimensions, but Hessian is different dimensions, because for it is taking this as a 2 parameters. So it is saying that for x1 we have this value, but we don't have x2, so it is 0. And similarly for now, it calculates for x1 first, which is 0, and for x2 it is 12. So that's why you have different dimensions. But if you pass only a single variable here, then you will get same dimensions, 24. So as you can see, like it is very easy to calculate Jacobian Hessian using Autograd library, right? And now let's calculate the Newton method using these libraries. Okay, let's move. Okay, let me run this again and remove this numpy thing from the import. Just calculate all the things same. Everything is same. Predict sigmoid, cross entropy loss, and now we get to this. So now instead of using this, I want to use something like Jacobian, right? And instead of using this, I wanted to use something like Hessian. So how do we do that? So first of all, the first function that you give it is something like weights, because you need to tell Autograd library that with respect to what you want to calculate your like differentiation, like with respect to what. So we are calculating with respect to weights, but as you can see, there is no loss function which have weights in it. Okay, so we can create a new function which only takes weights parameter. And like what it will be, like it is, we can first of all predict, wait a second. Yeah, just we can predict the values like this again, just from the weights. And we can calculate the loss using our above function only. Just to remove the confusion, let me just name it like this, otherwise. So this is the same function, just it is just giving us loss, but the main difference is that it is only taking one parameter called weights. You can have multiple parameters also, but there needs to be a parameter with which respect to what you want to calculate. Here we do not have weights variable, so that's why we need to give weights variable here. If we have weights variable here also, then we can also use this function. Okay, so now we need to calculate Jacobian. So I'm just giving it a name Jack because JEC doesn't look good. I can calculate Jacobian here of the training loss function. And similarly, like I can call Hessian, like Hess is nothing. So like it sounds like a snake. So I'm giving a name snake. Hessian, and similarly for the training loss. And now like you can simply do this Jack and snake weights. So we have calculated the gradient and Hessian with this. Okay, let's implement this. Train this and see the curve. So it's again the same curve, but this time you're like you don't need to know don't need to be the geek. Like you need to know all the maths. Like you can do this simple. And now let's calculate the accuracy. So now this time it's 0.94. And if we compare this with the scikit-learn implementation, it's 0.92. So we are better than scikit-learn. How cool is that? Let me tell you like why there is a difference between like 0.94 and our implementation is 0.9. So one difference is that we are using Autograd library, which uses reverse mode automatic differentiation. Let me just name it somewhere. So this is the thing that most of the libraries uses, like PyTorch, TensorFlow, like everyone uses this. Like this we will talk about later also. But I just wanted to point out that they are doing differentiation a different way. So in computer, we are using float 32 values. So some values cut off from the last. So because they are doing different way, so they get different values, little bit different values only because the last part is cut off. So that's why like there is a difference of this 0.94. Otherwise, like there is just no difference. There's just no difference. Okay. Some people were also using the, I think the num differentiation tool, something like this. Like, so they don't shout on mail. So I can also do this, also show with this ND. So there is a similar function, I think Jacobian. Jacobian. So you can simply pass in cost, and let's again like calculate for 4 dot, and let me just do this x cube for simplicity. Like if you do this as well, so you get same. So everything works. It's just a matter of what you want to implement. You can calculate Hessian also like similar, right? So similar. So I think we are done with this now. If anybody has any questions on it, please go ahead.